Welcome back to RoboFication for AI safety-critical systems. In the previous episode, we explored the importance of systems engineering in AI and autonomous systems. Today, we're going to focus on the system lifecycle stages of safety-critical AI systems, and by safety-critical, we mean AI systems that often operate in real-time environments where failure could result in catastrophic outcomes. These are systems used in industries like aerospace, autonomous vehicles, healthcare, and even industrial robotics. When we talk about the life cycle of a safety-critical AI system, we break it down into several stages: design, development, testing, deployment, and maintenance. But unlike traditional systems, safety-critical AI systems introduce a range of unique challenges that make each phase more complex. Design phase. Let's start with the design phase. In safety-critical AI systems, this phase involves much more than just translating operational goals into technical specifications. Here, the design must consider real-time processing, fail-safes, and redundancy mechanisms to ensure that even in unpredictable conditions, the system remains safe. Take autonomous vehicles as an example. The design of an AI-driven vehicle must account for numerous variables: unpredictable human drivers, changing weather conditions, or even sudden hardware failures. During the design phase, engineers must integrate not only AI models but also failover systems. In real-time systems, latency is key. If the AI model takes too long to make a decision, it could be disastrous. Therefore, the design must ensure that decisions are made quickly and that there are redundant pathways for critical tasks like braking and steering. In industries like aerospace, redundancy is a must-have. For example, the fly-by-wire systems used in modern aircraft must be designed with multiple layers of safety, ensuring that any single point of failure will not lead to catastrophe. The same level of precaution must be applied to AI systems used in autonomous air taxis or unmanned drones. These systems require a balance between high-performance AI and robust systems engineering practices to ensure that the system is safe, even when faced with failures. Development phase. Next, let's dive into the development phase. This is where AI models are built and trained. For safety-critical systems, this phase is especially demanding because the AI needs to be predictable and robust. Unlike consumer AI applications, where slight variations in output may be acceptable, safety-critical systems need to maintain accuracy under all circumstances. In this phase, engineers focus on developing fail-safe AI algorithms and ensuring that the system can handle unexpected inputs without behaving unpredictably. For example, in industrial settings, AI-driven robotic systems need to ensure that any failure in sensor readings doesn't result in harmful actions, such as collisions with human workers or equipment. This can be achieved through a combination of redundant sensors and real-time error checking that triggers corrective measures. The development phase also involves creating AI systems that are resilient to adversarial attacks, where malicious inputs are designed to trick the system. In safety-critical environments like healthcare, for instance, AI systems controlling robotic surgical tools must be immune to such attacks. These systems often employ defense mechanisms such as anomaly detection and secure hardware layers to prevent unauthorized interference. Another key component during the development phase is the use of real-world data. The datasets used to train AI systems must be comprehensive, representing all possible operational conditions. A common industry practice is to simulate various real-time scenarios in high-fidelity environments to ensure that the AI model is trained to respond to a wide range of real-world challenges. For example, the automotive industry uses advanced simulators to test autonomous vehicle software under various traffic, weather, and road conditions to ensure robustness before deployment. Testing and validation phase. Once the development phase is complete, we move on to testing and validation. In safety-critical AI systems, this phase must go beyond traditional testing approaches. It's not enough to test for functionality alone. Engineers need to ensure that the system can operate safely in edge cases and fail-safe scenarios. An industry-standard approach for testing safety-critical systems is hardware-in-the-loop (HIL) testing, where the AI software interacts with actual hardware components in a controlled environment. For example, in autonomous vehicles, the AI model is connected to the vehicle's physical hardware, like its sensors and control systems, allowing engineers to test how the AI reacts to real-time inputs in real-world conditions. This approach ensures that the system can handle unpredictable situations such as sudden mechanical failures or erratic sensor inputs. Moreover, testing in the safety-critical domain includes formal methods for verification. These methods provide mathematical guarantees that the system behaves as expected under all conditions. Formal verification tools are used to prove that the AI system adheres to predefined safety constraints, such as never exceeding a specific latency threshold during critical decision-making processes. This level of rigor is essential in industries like aerospace, where the margin for error is near zero. In addition to standard validation methods, stress testing plays a significant role in the industrial application of AI systems. For instance, in the oil and gas industry, AI-driven systems that monitor drilling operations must be tested under extreme conditions, including high temperatures, pressure fluctuations, and potential equipment malfunctions. Engineers simulate these conditions to evaluate how the AI will respond under stress, ensuring that it remains safe and operational. Deployment phase. Now we enter the deployment phase. Here, the safety-critical AI system is put into actual operation, but this doesn't mean the work is over. In fact, deployment is where continuous validation becomes critical. AI systems in real-time environments are exposed to ever-changing conditions, which means they need to adapt while maintaining their safety standards. A key challenge during deployment is model drift, where an AI system's performance degrades over time as it encounters new, unfamiliar data. To combat this, safety-critical AI systems must have built-in mechanisms for self-monitoring and model updates. In industries like autonomous aviation, systems are continuously monitored to detect any signs of performance drift. If detected, the system automatically triggers an update or recalibration to ensure continued safety. Real-time monitoring also plays a major role in sectors like manufacturing, where AI-driven robotics are used to optimize production lines. Here, engineers must implement feedback loops that allow the AI to continuously learn from new data while ensuring that it doesn't drift outside of safe operating parameters. This requires integrating monitoring systems that can detect anomalies in real time and trigger alerts or even shutdowns when necessary. Maintenance and continuous monitoring. Finally, we arrive at the maintenance and monitoring phase. In safety-critical AI systems, this is perhaps the most crucial phase for long-term reliability. After deployment, these systems require continuous oversight to ensure that they maintain their performance and safety standards over time. This phase involves the use of digital twins, virtual replicas of physical systems that simulate real-time conditions. These twins enable engineers to test updates and predict failures without disrupting the live system. In sectors like autonomous mining, continuous monitoring is critical. AI-driven vehicles and machinery operate in harsh environments, and failure could endanger both human lives and operational assets. Here, AI systems are equipped with real-time diagnostics that constantly assess performance and predict maintenance needs before a failure occurs. In addition, safety-critical AI systems must remain cybersecure. As these systems are often connected to networks, they become potential targets for cyber attacks. Engineers in sectors like autonomous vehicles and defense must ensure that their systems have end-to-end encryption and secure access control to prevent unauthorized tampering. Conclusion. In conclusion, the life cycle of a safety-critical AI system is far more dynamic and complex than traditional systems. Each phase, design, development, testing, deployment, and maintenance, requires specialized attention to ensure that the system operates safely and reliably in real-time environments. Whether it's autonomous vehicles, industrial robotics, or aerospace applications, the key to success lies in rigorous systems engineering practices and continuous validation throughout the system's lifecycle. In our next episode, we'll explore requirements engineering for autonomous systems, looking at how to define, measure, and verify the performance of AI systems that are constantly evolving. Stay tuned, and don't forget to like this video, subscribe to our YouTube channel, and follow us on LinkedIn and X for more episodes. Thanks for joining us on RoboFication for AI safety-critical systems. Let's continue building the future together.